Hello again, and welcome to the final hydrocarbon lesson that we are going to do, and that is for the alkynes. Okay, now the alkynes, I'm sure you can imagine, very much related to the alkanes and the alkenes. The only thing is alkynes are at least one triple bond between two carbons. Okay, so the simplest one would be what is called Ffine. That means we have two carbons, F, and since the two carbons have a triple bond, it gets the suffix -ine. So alkynes get the suffix -ine, and nothing else is different. That's the only difference. If you know how to name alkenes, you know how to name alkynes. Okay, so just to continue, what we will have, however, are two hydrogens. Since now I will have 8 carbons, 8 valence electrons for each carbon, valence electrons for each carbon. You've got 2, 4, 6, 8, 2, 4, 6, 8. So there's 8 electrons around each carbon, and hydrogen 2 each. So this is a basic structure for Ffine. Okay, so let's do a more complicated one. Okay, I'll try and make it as complicated as I can imagine. Okay, obviously it's a carbon, and this one has that, and the carbon here, and okay, yeah, I think that is good enough. Okay, so let me just fill in all my hydrogens. Okay, so I'm really just going all out, thinking up the most difficult one I can imagine, just off my head. And what I'm going to do is give this one its name. Okay, so what you should realize is that the moment there is a triple bond, that is called INE. Okay, some sort of alkyne. So now we just need to count what is the longest chain that contains all of the triple bonds. Okay, so I have to contain all of the triple bonds, which is 1, 2, 3, 4, 5, 6. So this must be a hex, because there are 6. Now I need to number, because you can see there's 2. Okay, I know that it's going to be hexadiene. Okay, hexadiene, and then I can also see, and now I need to number. Now you can see there's also alkyl substituents, but they do not get preference. The functional groups get preference, and this functional group alkyne, we need to number so that we first encounter a triple bond. So if I can see here, I've got a triple bond right on the end, so I'm obviously going to start here. 1, 2, 3, 4, 5, 6. So I've got a triple bond at 1 and 2, so at 1 and at 4. So this is hexa 1,4 diene. Okay, that is if it wasn't for the alkyl groups. Okay, so the alkyl groups are 2 methyl groups. So I know I will have 2 methyl, which is dimethyl. And now I just need to indicate the numbers where they occur, and since both of them are on 3, it would be 3,3 dimethyl hexa 1,4 diene. Okay, I don't think that was so difficult. You can see it's the exact same process for naming alkenes. So if you can name alkenes, you can name alkynes, and the only difference between naming alkenes and alkynes and naming alkanes is literally the suffix and the numbering to and the numbering to prioritize the triple and double bonds. Okay, now other than that, the only other thing I want to say about alkynes is that the properties remain the same. As the carbon chain increases, the length of the carbon chain, an increase in carbons, increase intermolecular forces, an increase in branches, okay, will decrease intermolecular forces. Okay, so that is important. Two elements that have the same number of carbons, but the one has, so for example, this one is 1, 2, 3, 4, 5, 6, 7, 8. Okay, but it's not an octadiene. Okay, it's a hexa because two of the carbons are in branches. So even though both of them might have C8 carbons, because the one has branches, the intermolecular forces will be less because the surface area of two molecules that can get in contact is less. Okay, the branches are getting in the way for the things to be more compact and therefore better attractive. Okay, so that stays the same, and the other thing that we also need to just mention is that this is unsaturated. In other words, we can saturate it by adding hydrogen, and when I do that, okay, this process is called hydrogenation. Okay, so I'm just treating a bunch of topics in the same video because it's simply a repeat of what happened with the alkenes. The same thing happens with the alkanes. So let me give the easiest one I can think of, okay, as an example, just to show you that the one difference when we do this, okay, hydrogen producing a saturated, in this case we have ethine, and we will produce ethane, okay, and I just want to show you the problem is here we have 6 hydrogens. We have 6 hydrogens, and on this side we only have 4, okay, hydrogens, which means we will need more than just one diatomic molecule for hydrogen. We will need 2 of them. So that's the only difference here, is there's not just one bond to break, there are 2 bonds to break. So when that bond break, we need 2 hydrogens, which one diatomic molecule will provide, but since there's another bond that needs to break, we need another diatomic molecule, so we need 2 diatomic molecules, in other words an additional 4 hydrogen atoms to react here. And that's the only difference really when it comes to the hydrogenation of alkynes, and that is really the only extra thing I wanted to say. I think I'll say one more thing, and that is the general molecular formula. We know for alkanes the general molecular formula is CnH2n plus 2. Okay, this is for alkanes. Okay. Now alkenes have 2 less hydrogens, okay, because they have one double bond, at least one double bond. So they have, for every double bond, they have 2 less hydrogens. So let's assume there's only one double bond. Then of the hydrogens, we will lose this +2 because those 2 will come together. Okay, so we'll lose 2. So for alkynes, we will lose another 2. So for every carbon, we will have 2 hydrogens, but we will subtract 2 in the end. So just to show you that this is the case, here we've got 2 carbons, so we've got C2, and if we multiply 2 with 2, we get 4 minus 2, which is 2. So if I were to do, let's say, octane will have a double bond, a triple bond between the first carbon and the second one, and then there will be another 6 carbons. So octane's general molecular formula would be C8H. Now what do? We double this and subtract 2, so it's 16 minus 2 is 14 hydrogens. In total we'll have 14 hydrogens. So if we do our hydrogenation, okay, we will from an octane produce an octane, which is C8H. Instead, octane we would multiply by 2 and add 2. So this would be 16 plus 2 is 18. And here we can see we've got 18 on this side and only 16 on this side. And again, we simply multiply this by 2 because we need 2 diatomic molecules to break the 2 extra carbon bonds that we have here. And that will again balance this equation. I think that's enough said about the alkynes. They're not very difficult, they're not very common, but they are very simple to deal with when you get them. So good luck, I'll see you in the next video.